And so we are studying solubility equilibria. Yesterday, or whichever day you watched the previous lecture, we had gotten through a bunch of examples. So here's the last example that we're going to do. So what volume of water would be required to completely dissolve 10 grams of silver sulfate? So you should have your KSP chart. And let's start with, oh, no Griffin for colors. What's the equation for the dissolution of this? I'm going to the cards. Go from the middle. So, Wendy, what is the equation that we're going to be looking at? All right. Now, on your KSP sheet, what is the value for this? Yeah, GG. 1.2 times 10 to the negative fifth. Okay. So, how are you going to solve this problem? What might we be able to do to figure out how much water we would need? Yeah, go ahead, Alex. So you are going to have to find a concentration. But that's not exactly how we're going to do it. But good thinking. Yeah, Alex. There we go. So, yeah, we're going to backtrack. So we're going to find the concentration at saturation using this value in this equation. Then, once we have that, we can figure out how many moles per liter. We convert this from grams. We convert this from grams to moles and go from there. Okay? So how about you guys solve for what is the concentration at saturation for silver sulfate? So I want you to look at it, do it, just part one, and figure out how to make it better. So this is like your child development class. This is like your teaching class. So try the whole thing, see what makes sense and what doesn't, and then tell me, like, make some notes as to why it may or may not make sense. So you'll need, like, it's pretty straightforward. You shouldn't have any questions. Is that cool? All right.
There happens to be an emergency in the next like 60 seconds while I'm doing it.
That's fine. There should be some over here.
I took them.
Okay. Yeah. Oh, I thought you meant here. So wait, you don't have a calculator either? Because Nora doesn't have a calculator. All right, so you guys are on the right track. I'm walking around. A bunch of people are on the right track. You should have gotten at least to here. Okay, so the trick here is what Wendy said, the 2 Ag plus. So it's not plus x, it's plus 2x. So KSP is equal to the concentration of Ag plus squared times SO4 2 minus. So what was the value again? 2 times 10 to the minus 5 equals 2x squared times x. A lot of people forget to square the 2, so they'll write down like 2x cubed. But it's 1.2 times 10 to the minus 5th equals 4x cubed. So what does x equal? Do people agree? Okay. So this is, my solubility is 0.0144 moles per liter. Because the concentration of the question was, why isn't it just 2x? Why is it 2x squared? It's because you have twice the amount of ions of Ag as you do of sulfate. So like if I had 10 ions of sulfate, I would have 20 of silver. So I plug that value in here, which automatically has to be squared anyway. Yeah. Okay, so there are 2 ways we can do this. So you can do it that way, which is you find the number of moles that you have, that 10 grams is, and go from there. I'm going to show you a slightly different way. Okay? So, whoops. Oh no, where'd it go? Uh-oh. No. It erased everything. Control Z. Uh-oh. Oh, no. Yeah, and this is all in the lecture, too. So, oh well. Sometimes you gotta redo stuff. All right, Ag2SO4. For those of you watching live, I apologize. This is going to take a minute. All right. So if you're watching it live, guys, if you're watching it at home, I cut things down very quickly. I cut out some of the stuff, so the original is better. Now, you have 0.014 moles per liter. Now, you can change this to grams per liter. How can I change it to grams per liter? Find the molar mass of Ag2SO4. So 1 mole. Does anybody have that on hand? It's big. What's that? Oh, I think it's more than that. 311.8? 311.8? All right. 311.8. So that gets rid of moles. So now I have grams per liter. Well, I know I have 10 grams. So what am I going to need to do to find liters? So, well, let's just solve this first. What do you guys get when we solve this? 4.489? Let's do 4.49 grams per liter. Well, I know I have 10 grams of AgSO4. Sorry, Ag2SO4. And this is just a ratio again. Bless you. Grams cross out, and I get liters. So I get 2 point something. 2.27 liters. Somewhere along those lines. So I solved for X, which told me my solubility. I found my solubility in grams per liter, and then I converted it to liters. Conversely, you could just take your 10 grams and convert it to moles. Okay. Questions about this? Because I see blank stares. Maybe people are just tired. Or my new monotone voice is putting people to sleep. Okay, so the question was, on tests or APs, will it tell you to refer to a number or should you just know? On the AP or quizzes, you will be given the number. So on quizzes, we'll tell you to look at your sheet. Tests or the AP exam, it will give you the number. Or maybe tests will give you, but most of the time it'll be put right there for you. All right. Not only were students playing games, they were playing very loudly and distracting me. Okay. So here is the solubility common ion effect. So far we've only looked at salts in pure distilled water. Now, a lot of the times that is not going to be true. So there might already be some things in the solution that will affect the solubility. So when looking to dissolve salts in a liquid with other ions present, you have to look at ions that are in both the solution and the salt. So if you try to dissolve an insoluble salt in a solution containing a common ion, well, you already have some of that ion there. So it's going to push back and cause the solubility to decrease. And this can be seen using Rice charts. We're going to compare compare salts in pure water to salts in solution. Okay. So this is thing you should know. 23. When a common ion, oh, God, I'm so sorry, my robot voice. When a common ion is added to the solution, an ionic compound becomes less soluble. So I want you guys to try on your own to figure out how you could solve this problem. Talk at your tables. How can you figure out this problem? I will give you a hint. Think food. What's that? You're used to it, and yeah, it's Mr. Hamill's. So I have a student who captions B block sometimes, and she said she could already tell I was so much easier to understand the way I talked yesterday, which sucks because it's so painful, but right. they don't. I don't know. No one's gonna do that. I think I will. I think I will mess with some. At some point, I'll just throw something in and mess with people. All right, focus on this. Like, I'm gonna walk around to see if anybody's. Edward's got it. Our first person has got it. That has I've heard. It's take your time. Take your time. Hasn't even written anything down. Okay. And we're back. All right. Edward, because you were the one who figured it out, tell me what to do. Your initial concentration of Cl minus should be 0.1 because you already have 0.1 NaCl hanging out, so you have this already. So plus X plus X. Now what's our KSP for AgCl? Very tiny, right? At 1.6 times 10 to the minus 10. So these problems are actually a lot easier because now I have X, but doesn't matter, so it's 0.1, right? Because this is negligible. So now I can plug 1.6 times 10 to the minus 10th equals Ag plus times Cl minus. 1.6 times 10 to the minus 10th equals X times 0.1. And if I do my math right, divide both sides times, I get 1.6 times 10 to the minus 9th is my solubility of AgCl in this solution. Now, if you go back to, oh yeah, Ian, and then, can you assume the NaCl fully dissolves? Yes. Yes, so normally they're going to be soluble salts, right? We're not going to make it a thing where you have to calculate the solubility of one and then another, like, well, on a problem set we might do that, but yeah, Carter. Just the question is, what does molar solubility actually mean? It's how many moles you can dissolve per liter in solution. So here, your unit here is moles per liter, right? So when you solve for X, you're solving for moles per liter. The question is, what is the difference between molar solubility and molarity? Molarity, you can have any amount of molarity, right? The molar solubility is the peak amount, it's the maximum you can fit. So you can have anything less than that value in solution. Alexa, do you have your hand up? So the question is, if you have two salts that don't share any common ions, do they not affect each other? So we're going to say for us that that is true. So it might not be true in practice, but theoretically, ideally, it does hold true. Now, previously we solved this value for pure water. And in pure water, I think X was 1.3 times 10 to the minus 5. So just by adding that 0.1 molar solution of NaCl, my solubility dropped by 10 to the fourth. So adding a common ion can have an enormous impact on the solubility of a salt in solution, right? 1.3 times 10 to the minus 5th versus 1.6 times 10 to the minus 9th, just by adding in 0.1 molar NaCl. Now, this makes sense if you think about it in terms of Le Chatelier. Oh, I'm so like self-conscious about that, saying that word now. Le Chatelier. That's just like too over the top. Le Chateliers. So if you think about that dude's principle, right? If I'm adding Cl into this equilibrium, if I add Cl in, it pushes back to the reactant, right? So by that dude's principle, adding in Cl minus shifts back to the reactant. So it makes sense that my molar solubility is a lot lower. Yeah, Alex. Oh, this is in pure water. So this is the solubility of silver chloride in pure water. This is the solubility in 0.1 molar NaCl. So it's, 10 to the fourth, what is that, 10,000? 1,000? 10,000. It's 10,000 times less soluble in this case. Okay. All right. We can also have a basic salt react with an acid, so it is more soluble. Now, question from the slide before. Where did I get? Oh, the question was how did I get the 1.3 times 10 to the minus 5th on this slide? We solved it previous. It's on like the second page. So we had already done it. So we're looping back to something we already did. So, yeah, it was on slide... the second page. Yeah. So I didn't just pull that out of nowhere. Yeah, we did it yesterday. Okay. Now, why does pH affect the solubility of magnesium hydroxide? So, let's look at what's happening. Okay. So, if I react it with an acid, so I get this reaction that also happens. All right. Well, let's talk about it conceptually for a minute. If I add base, if I add in base to this equilibrium, the top equilibrium here, if I add in OH minus, what's going to happen to my solubility of magnesium hydroxide? So if I increase my OH just by that dude's principle, if my OH minus goes up, what does that mean to my solubility of MgOH2? It goes down, right? I'm going to have more solids, so my solubility goes down. But now, if I react it with an acid, I have this other reaction that occurs. So the acid will react with the OH minus and make 2H2O. So let's look at it in terms of KSP. What's my KSP for magnesium hydroxide? From our sheet. I think it's on there. All right. So let's go back to thermo. Is this reaction thermodynamically favorable? Ooh, we need to know this. You know, you have a cumulative coming up in not too long. Delta G is positive, so it is not favorable. Anytime you have a negative exponent on your K value, it's not favorable. But, so that means this reaction is not thermodynamically favorable, but my K for this reaction is 1 over kW squared equals 1 over 10 to the minus 14th squared equals 1 times 10 to the 28th. Is this reaction favorable? Very. That is a large K value. 14. Because it's 1 over kW squared. Okay. So what we're doing is we're coupling an unfavorable reaction with a favorable one to increase, in this case, our solubility. How would I find the overall K value for my overall reaction? Yep. So the correct guess is it's K1 times K2. So K1 times K2, which is equal to 8.9 times 10 to the 16th. I still end up with a very large K. So now my overall reaction is very favorable. So if you want to look at it conceptually, what's happening is as soon as you make the hydroxide ion, it reacts with H plus and it sucks it away. So what does that mean is constantly happening to this value? It keeps going down and down and down. So for those of you at home, I'm talking about the OH value here. So if this keeps going down, which way does my reaction keep shifting? Keeps shifting to the right. And so whereas before I wasn't really dissolving very much, now I get more and more of my MgOH2 to dissolve because I'm taking this OH minus out of solution. Mathematically, combining the two reactions gives you a very large K, so you know that now you take an unfavorable reaction and make it favorable. And you can calculate any of these values for equilibrium. Okay. All right. So here's some of our learning objectives from back when. Student can use, why do they keep putting his name in? Principle to make qualitative predictions for systems in which coupled reactions that share a common intermediate drive the formation of a product. So let's just look at this for a second. The intermediate is OH minus, right? It doesn't show up in my overall reaction. It's produced in the first one and consumed in the second. So what this means is coupled reactions that share a common intermediate, in this case the common intermediate of OH minus, allows this reaction, which was previously unfavorable, to become favorable. And the student can make quantitative predictions for systems involving coupled reactions that share a common intermediate based on the equilibrium constant for the combined reaction, which we did right here on the right. Yeah. What about acidic salts? So we're going to talk a little bit about, the question was, what about acidic salts? So the converse would be true, right? You would react it with a base, but I'm going to show you a weird instance in a little bit. Okay. So what is the molar solubility of tin hydroxide in a 0.1 molar HCl solution? How does it compare with the molar solubility of tin hydroxide in pure water? So let's do our reactions first. Somebody shout a color because Griffin's not here. Purple. I heard purple. We'll do orange next. All right. SnOH2. SN2 plus. Sorry, this is solid. AQ plus 2OH minus. AQ. So this will be the reaction that governs the molar solubility in pure water. We'll call this K1. But if I put it in an acid, what reaction is going to happen? So I have 2OH minus plus 2H plus makes H2O liquid. And this is our K2. And this is in acid. Actually, this is just neutralization. So Zach, tell me my overall reaction in acid. Yeah. Okay. So, what information do we now need? So we need the KSP of tin hydroxide. So, which is, from our formula sheets, very small. Okay. And now, my K for this one is the same thing we did before. Okay. We flipped our KW for this reaction, and we have it twice, so we square it. So K, my overall K, is equal to what? This you should be able to do in your head. $30. Okay, so on the next slide, I want you guys to calculate the molar solubility of tin hydroxide in pure water. And then try it in HCl. So if you multiply k1 times k2 together, so 3 times 10 to the minus 27 times 1 times 10 to the 28 is equal to 30. Is it all looking familiar?
What?
Is it looking familiar?
It is. It's always I do. So I always kind of
Mm-hmm.
and like I have this one in particular that plays a lot of like restaurant rugby and Marcello's, and she like matches very nicely to like.
Oh, really?
There's a lot of like swells.
Mm-hmm.
Like it makes it a lot more dramatic. You guys should think about producing a movie.
The Chem Lecture movie.
Yeah. With some live action parts.
Irene, have you met Lisa? Lisa, Irene. So Lisa TAs this part. She did not take the nap this morning that Irene. Satsumishite. Explain. I'm sorry. Oh, wait, what? I liked it. You've made the common mistake. It's 2x squared. So it's 4x cubed. But otherwise, it's fine. No, that's right so far. It's not. I'll walk you through. Okay, guys. I saw some really good stuff happening, but not perfect stuff happening in a lot of cases. So, right here, my initial. The trick, guys. This is in pure water. So KSP equals 3 times 10 to the minus 27. I start with 0 of each, plus x, plus 2x, So my KSP equals 3 times 10 to the minus 27th so 4x cubed equals 3 times 10 to the minus 27th. So solving for x, you should have gotten 9.1 times 10 to the minus 10th. That is your molar solubility of tin hydroxide in pure water. But now when we put it in 0.1 molar HCl, we're using a different equation. We're not using this same equation here. We're using our combined equation from the previous slide, which was this. Okay. Now, I have good news and I have bad news. The good news is I can cross off 2 of these things straight away. That's the good news. I'll get to the bad news in a second. Other thing is your initial concentration of H plus is 0.01. I have a strong acid that completely dissociates, so my H plus is 0.01. My SN2 plus is 0. So I'm going to lose 2x here. I'm going to gain x here. So equilibrium I have x. Well, my K was 30. So what's the bad news? It's not negligible. So my overall K expression for this reaction is just the tin ion over H plus squared. So 30 equals x over 0.01 minus 2x squared, which is a quadratic. So you'll never get something like this on a test or a quiz. So x equals 0.015 molar. So what this is saying is I'm 100 million times more soluble in point. Why am I soluble? Tin hydroxide is 100 million times more soluble in 0.1 molar HCl than it is in pure water. That's a big difference. Okay. Okay. So most of problem set 20 is this. But we're going to talk a little bit about complex ion formation. So we've seen these a little bit. We saw these when we did our equilibrium, our short little equilibrium lab. Remember where we were changing the blue to the pink, and it was cobalt chloride, and then it was COCl4 2 minus. We had a lot of different complex ions going on. So complex ions are, they tend to be large ions with a metal ion in the middle. What's that? Right. Surrounded by what are called ligands. Now, in chapter 17, we gave you the teeniest, briefest overview of Lewis acids and bases. The equations that we showed you were mostly complex ions. So I'm going to show you some pictures in a little bit, but the metal ion is positive, and it actually accepts lone pairs from these ligands. So it's a Lewis acid-base reaction where the metal ion acts as the Lewis acid and the ligand acts as a Lewis base. And a ligand is a molecule or ion that can share lone pairs. So the metal ion is positive. It's attracting the lone pairs from a molecule or ion, and they actually stick together. You saw one of these a bunch in seven, maybe not a bunch, but aluminum. Why is aluminum acidic in water? Right. So aluminum, what's that? Yeah, this is aluminum hexahydrate. But you don't need to know the names. Aluminum, if you put aluminum in water, it's got a charge of 3+. So it attracts the lone pairs from the oxygen on water, and they stick together, and they form a complex ion. So you can imagine this complex ion is much larger than a normal ion. So what makes a good complex ion? Transition metals. Transition metal ions. So the ones you'll see iron, you'll see silver, you'll see copper, and then aluminum is the other one you'll see a lot. So now, these aren't the only ones that can do it. In the body, I'm going to show you some examples in the body, but aluminum is small and very positively charged, so it can attract very, very tightly. These other ones, I don't know how much I buy the explanation that, oh, they have empty orbitals that can be filled, but we're not going to make you memorize the ones that make. Oh, someone might be going up on the wall of shame. Such. All right. So, good ligands are things like water, and I'm going to put the lone pairs here. NH3 and Cl minus. So water is very partially negative on the O. Ammonia is partially negative on the N with that lone pair. Cl minus is a negative ion with these lone pairs. So they can attach to the central atom. Yeah, Ian. Ligands can, the statement was ligands can also be called Lewis bases. Yep. How about, the question is, how about NO2? Maybe. Maybe. These are the ones that are the most common that you'll see, but I'm going to give that one a maybe. The question was NO2. Now, one of the things I want to try to build in future years is more applications. So this is kind of abstract. So let's make it less abstract. Hemoglobin is really a complex ion. So for those of you who have taken, all of you should know this except for my one or two people who haven't taken bio yet. What does hemoglobin do? Okay, seniors, what does hemoglobin? Oh, wait, Joanna. Yeah, so hemoglobin carries oxygen around the red blood cells. Not just does it carry oxygen around the red blood cells, it also gets carbon dioxide out, right? So hemoglobin is really your gas transport system in the body. So what happens is I have this large molecule with a positively charged iron in the middle. It will take oxygen, so the lone pairs from oxygen will bind to the iron. It will carry it around your body to where it needs to go, and then offload it and carry CO2 out. So this is a complex ion that is really, hemoglobin's really a protein. It's like a much larger molecule than we're going to see in this class, but this is a very important one. Yeah. Mm-hmm. Yeah, the question was about iron deficiency. I would imagine, I'm not a biologist, I would imagine that, right, with iron deficiency, you're not going to be able to carry your oxygen, like the hemoglobin won't be able to carry your oxygen around as easily. I think there are other needs for iron in the body, I believe, but this is maybe the most common. So what is the common case study with problems with hemoglobin? What's the disease that? Sickle cell anemia it's hemophilia is one thing, but sickle cell anemia is the one that is always the case study in every biology class with hereditary genetics and stuff like that. It's very simple to track, right? Like, so if you have sickle cell anemia, one of the things about hemoglobin is the shape of the molecule. So you get conformational changes carrying oxygen or carbon dioxide. But sickle cell anemia, your hemoglobin cells actually, or your red blood cells, right, that carry the hemoglobin actually change shape. So you get all kinds of different problems. So, all right, that's hemoglobin. Another one is EDTA, which I had to write down the name of. So it is ethylene diamine tetraacetic acid. Now, this is not a biological agent like hemoglobin. But this is actually really important for us. It's called a chelating agent. So what we can do is we can put EDTA into water, and water that has maybe some ions in it that we don't want it to have. So what will happen is the EDTA will surround the metal ion, effectively taking it out of solution. So if I have something that I don't want in the water, say iron or lead. Lead's a perfect one. So say I had lead in water and I want to get rid of the lead. I put in some EDTA. The EDTA creates a complex ion with the lead, and now all of a sudden that lead is no longer pure lead in your solution. You're left with something that is no longer toxic or something that you can easily remove. You can. So the question is, do you then take out the EDTA? I think you can take out the EDTA, or it just makes it such that you don't need to worry about it anymore. So the EDTA will hold on to the central atom. That is correct. So the question about this is this is the left-hand side is EDTA naturally. The right-hand side is how it surrounds the cation, the metal cation. So like this reorganizes itself. The left-hand side reorganizes itself around the metal ion. So the question was, can you drink the water? Is that if you put EDTA in it? I do not know the answer to that. So that would be something to research. I wouldn't just do it. Like, oh, I have some nice leady water, and I'll throw it. Right. But yes, they use this for wastewater treatment. So but I don't know if they leave it in or take it out. What's that? Right. I think it's probably just part of the process that they then take out. Oh, so the question is, why are there no H's over here? So this is, I told you it was tetrafluoroacetic acid was part of it. So that's when the H's have been deprotonated on the right. So it's gone. The H pluses have gone into solution. Good question. So tetrafluoroacetic acid, I think, is kind of a pretty strong. Oh wait, not tetrafluoro, just tetraacetic acid. So I don't know. I don't know what the pKa of each of those would be. But tetrafluoroacetic acid's crazy strong. But you can have tetrafluoroacetic acid. Oh, yeah, you're right. Let me think about it, and I'll come back to it. I don't want to get hung up on that. Positive. Cation is positive, right? Okay. Okay. So those are just two examples. But the formation of a complex ion can remove a metal ion from equilibrium, making the compound more soluble. So silver. Here's a very popular one that comes up a lot. Silver and ammonia. So I have my silver ion. Notice the lone pairs from ammonia are attracted to the silver ion. And so here's my central atom. And here is one ligand. Here is another ligand. And here's my overall chemical equation. So this can actually dramatically increase solubility. And we can describe them, unsurprisingly, because we put it in here, using equilibrium expressions. So our final K, I think it's our final K of the year, the equilibrium constant is called Kf for this reaction, for K of formation. And they are very large. If it's very large, what does that imply about the favorability? Yes, these are very favorable reactions. The K is large, the delta G is negative, so these are very favorable. So, for example, this, the one I just showed you, has a Kf of 1.6 times 10 to the 7th. So how do we use this? So, back to silver chloride. What is the molar solubility of AgCl in a 1 molar solution of ammonia? Well, let's start with our first equation. What's our first general solubility equation? Let me go to the cards. Thomas, our first general solubility equation for AgCl. Okay. So we have, this is our reaction 1. Well, now, if I put this in water and I'm making Ag+, I can also have this reaction. So Lexi, what would my overall reaction be? Excellent. getting my AQs. So again, we have a common intermediate. In this case, it's not H plus or OH minus. It's the silver Ag plus ion. All right, so my K1 is my KSP. So what's the KSP for silver chloride? 10 to the negative 10th. My KF was that also, it was like, so my overall is KSP times KF, which I have written down, but Edward's going to tell me in a second. (2.56 times 10 to the minus 3). All right. Okay. I got, yeah, that's fine. So the question is, why is it 2NH3 right here? Because that's just the reaction that happens. So for these, it's when you get to higher level chemistry, these KFs, you can predict how many ligands they will attract. But for us, we're going to give you, we'd either give you this overall equation or we'd give you what the complex ion actually is. So you know. So like this could be like AgNH3 6. So you would know it would be 6 NH3s. Okay. Now, there's not a lot of space here. Hold on, let me check. Because I had, oh, good, I added another slide. I made a note to myself to do that, but I didn't on here. All right, so we have our overall reaction. All right. So I want you guys to calculate the molar solubility of AgCl under these conditions. So take a few minutes, work it out, talk to your neighbors. Won't you be my neighbor? What the kids going outside today? What do you think? So me that this. All right, cool. Thank you. How was your trash project? Mm-hmm. Seems fun. It's fun. Well done. Well done. Yeah, I can imagine. So you don't need to solve a quadratic. Take the square root. I'm always thinking. All right, so chemists, you guys are working hard. Unfortunately, we're shorter on time than I would like to keep you guys going and solving, and I think most people are on the right track. But I want to go through it just in case. So the only thing we can cross out is the AgCl. So I'm going to start with 0 and 0. What do I put in here? 1. So as this reaction happens, I lose 2x here, I make x, and I make x here. So I have 1.0 minus 2x, and I have x and x. Now this is where it gets messy, because my k is not small. Not small enough. But it's actually not as bad as you think. So k equals all right. So I plug in x for both of these on the top, and I get x times x over 1.0 minus 2x squared. So I get x squared over 1.0 minus 2x squared. So now I'm going to plug in my k value, which we saw was 0.00256 equal to x squared over 1.0 minus 2x squared. Now this looks super duper ugly. But what can I do that would simplify this dramatically? I know we talked about it already. What can you do to simplify this expression dramatically? Take the square root of both sides. Good. So instead of that, you get x over 1.0 minus 2x equals, and I have my number's slightly off, but it should be like 0.05. 506 now, so I do have the right number. So now it is no longer a quadratic. Still messy, but not a quadratic. So if you solve this out, you get x equals 0.046 molar. Now, compared that to what we saw initially with silver chloride, which was 1.26 times 10 to the minus fifth. So by adding ammonia, my silver chloride becomes a lot more soluble. Okay, we are almost done. It'll take 20 minutes tomorrow, and we'll be done lecturing for the year.